of superconductivity. And I thought that was a pretty informative video to give you a background of what's really happening in inside of what's really happening. What are the experimental phenomena that we can observe in superconductivity? And mainly, there are several things. First of all, we find that the resistance drops down to 0. So now if I were to plot the resistance as a function of temperature, resistance is something like, and this would be like a per unit length resistance, okay, per unit area. Then the expected graph looks like something like a linear relationship towards the very low temperatures. So this is 0. Okay. So we expect something like this towards very low temperatures. But what is experimentally found is in 1930, around the 1910s, I don't remember which year it is, maybe 1911. So Kimberley owns. He cooled down this. He cooled down the. I think the material was lead or something, and he cooled it down so much that he found that the resistance goes pretty much linearly, and then suddenly there's a drop, and then it's no longer detectable by the instrument of the day. The resistance is no longer detectable by the instrument of the day. So this was when they discovered this phenomena of superconductivity. And then later, when people started doing some thermodynamic experiments, they found that, okay, this point, which for lead may be around, I think, 7 or something Kelvin, but for aluminum it's like 3 Kelvin. For all the metals that we're going to be talking about today, this point is no higher than 20 Kelvins. Okay, so this is called the critical temperature of the superconductivity. And they found through some thermodynamic measurement by looking at the specific heat, they were able to find that this condition is associated with a phase transition. So people term the superconducting phase of metal. And this is this is one thing. So resistance dropping down to 0 is one thing. And the other thing that later talked about in his video is the so-called Meissner effect, which is to say that the superconductor, when it gets cooled down below this transition temperature, it expels magnetic field. Okay. So what we are able to deduce from there is that, well, superconductivity happens at low temperatures, and it has something to do with magnetic field. And from this hint, people started to think about, oh, this probably has something to do with the spin of the electron. Okay. And then there's also another important discovery, which is called the isotope effect, which is to say that the electron, the superconducting temperature, this critical temperature, is related to the mass of the ionic lattice, or impurities in the lattice. If it's more massive, then it turns out that I think the temperature drops as the ionic lattice becomes more massive, while the charge property stays the same. Okay. So that's called the isotope effect, and that gave people like Bardeen and Froelich some hint that superconductivity probably has to do with phonons in the lattice vibrations. And now nowadays for the metals that we're concerned with, which is aluminum, lead, maybe also what's that? Nickel, yeah, something like that, and some alloys of it. The classical, so-called classical picture, okay, of superconductivity, classical superconductivity. Okay, this is explained very well by the BCS theory, okay. And this theory came out actually on Green Street. Okay. So Bardeen, Cooper, and Schrieffer. All of them were at the time at our physics department here, and they won the Nobel Prize in 1975 or something. Okay. So today we're going to be looking at these classical superconductors, and by classical I mean they're explained by the BCS theory. Okay. Now later in the 1970s and the 1980s, people found so-called these exotic superconductors, which are not very well described by the BCS theory. And they have transition temperatures as high as maybe 80, 70 Kelvin-ish. Okay? And those we're not going to be talking about today. And I think up to date, there's still not a very satisfactory theory, microscopic theory, to describe them. And also today, we're not going to be looking at the full detail of this BCS theory, which is a sort of a microscopic theory for these classical superconductors. I'm just going to I'm just going to explain several aspects of it. So one thing is we said that these, the reason for high superconductivity is this electron-phonon coupling. What happens is actually two electrons, when they're both coupled to the ionic lattice, they get this attractive interaction, okay, by the exchange of virtual phonons. And I'm going to consider this by using an analogy where two dynamic variables is coupled through a simple harmonic oscillator. And we know from quantum mechanics that phonons can be thought of as simple harmonic oscillators, right? So I'm going to show you that if two dynamic variables are coupled through a simple harmonic oscillator using a very, very simple classical calculation, then we find that when we Fourier transform this coupling, the Green's function for the coupling, we see that there's a possibility for attraction, also a repulsion as well, depending on the energy exchange between the two systems and the natural frequency of the oscillator. Okay? So and then we're going to show you the electron-phonon interaction Hamiltonian. And when we quantize the Hamiltonian, you'll see that the form looks exactly like the simple harmonic oscillator coupling. So now if we went ahead and quantize this simple harmonic oscillator coupling in detail, and we take out the effects of the lattice, so to arrive at the effective electron-electron interaction, then we can see that electrons and electrons can couple attractively. Okay? But that's going to take a lot of time, which we don't have today. Okay? So once we explain this electron, that there is a possibility for electrons to be attracted to other electrons through coupling to the lattice, then I'm going to show you this problem of Cooper instability, okay? Which is to say, so long as at very low temperature, so long as there is some process by which electrons can be attracted to each other, then the electrons will form pairs. And this pairing effect, which is the instability of the normal state of metal, which is like a Fermi Sphere. Okay? And this pairing effect is what gives rise to superconductivity. And from this very simple consideration, we can take a look at what is the energy scale associated with this, the superconducting transition. How much is the energy of the system dropped? And also we can look at a critical temperature, an estimate of the critical temperature based on this temperature drop. So essentially, what's going to happen, in the end of today's lecture, I'm going to show you that, okay, so for the superconducting phase, if I were to draw an energy diagram, okay, and I'm going to call this K, and I'm going to call this is E, okay? And I'm going to put the Fermi energy at 0, okay? So what is in free metals, okay? In metals, we think about electrons as being free, so they have a quadratic energy diagram, okay? So close to the Fermi energy, the energy diagram is going to look like this, okay, for the electrons. And then we know that it's going to look like, when I flip this thing, it'll look like this for the holes, right? Okay. So what happens is we will find a solution to a Schrodinger equation that I'll write down that has a state over here, okay? And we will deduce what is this energy, what is this band gap, okay? And then we will also find, basically when the temperature is high, we'll see that when the temperature is so high, such that electrons that fell into this state can be excited thermally to the band above, and the superconductivity is no longer possible. Okay. So it's a very simple picture, much like when you have a semiconductor, and when bands starts to form, okay, when the electrons can be excited to the band above. Of course, in semiconductors you have conduction in that case, but in superconductors we'll see that superconductivity is destroyed there. Okay. So that's where we are going for today. All right. So I'm going to first be talking about the Fermi Sphere, which is a model that describes pretty well the normal state of the metal. Okay. So in the solid state physics, the simplest picture that we can use to describe a metal is that of a bunch of free electrons. So, free electrons. And each of the electrons is treated as a plane wave, and we completely ignore the effect of the Coulomb interaction between the electrons and the periodicity and the vibrations of the lattice. Okay. Each of them is described by a plane wave, so I may write a plane wave of wave vector k for an electron. That's equal to 1 over square root of omega. Omega being the size of the size of the solid, and then the plane wave is of course just this. But of course, the electron also has spin, so we know that this plane wave must also attach a spinner to it, and the spinner is typically denoted by something called chi, and we know that chi in the two-component representation of spin is like maybe alpha and beta. Okay, so that's the free electron in the simplest picture of a metal. So, and we know that there's this thing called the Fermi direct statistics. Okay, which tells you how the electrons will arrange themselves if we have a bunch of electrons. So the Fermi direct statistics come from the Pauli exclusion principle, which says that no electron can occupy the same state. Right. So if I draw a diagram with respect to energy of the probability that some state is filled, and this probability is, as you remember, a temperature of energy and a function of energy and temperature, right? So the system will want to lower, to possibly lower its energy at very low temperatures. So it starts from 1, okay, and it ends up being 0. And in the middle, it goes through something like this. And there is a point that we know is going to be at probability 1/2, which we call the Fermi energy. Okay. And when the temperature goes down to 0, this shape approaches a step. Okay. So basically, at 0 temperature, so I will label this with T equals to 0K. At 0 temperature, the picture is that the electrons are going to arrange themselves to occupy these low energy states one by one, and then they fill all the way up to the Fermi energy. The Fermi energy is the energy at 0 temperature of the next electron put into the metal, roughly, right? So we can relate this Fermi energy to the total number of electrons per unit volume inside of the metal. Right? So that would be if I were to do some counting. So this number of electrons per unit volume, okay, this is equal to, in general, it's going to be an integral. So there will be a factor of 2 coming from the spin degree of freedom, right? And I integrate from 0 to infinity. Actually, integrating over the energy, multiplying by the probability that this energy state is occupied and the density of state. Okay. So now at 0 temperature, we know that this is replaced by a step. So it basically replaces this integration limits to replace the upper limit of EF. Okay. So we can find the density of state for these massive particles with this kind of relation. The EK relation for the free electron is E is equal to h bar squared k squared over 2m. So we can derive the density of state from here, and then integrate the density of state from 0 to EF related to the total number of electrons, and we can find what is EF. Okay. So the density of state is 3D, and this is the single spin density of state. Okay. This is something like this, and then 2m over h bar squared 3 Okay. So if we do that integral, we find that the Fermi energy is equal to 3 pi squared n to the 2/3, and then there's some factor in the front, and it must be h bar squared over 2m because this is an energy thing. Okay. So that's the Fermi energy, and then we can also find out things about, well, at 0 temperature, what is the highest velocity of the electron if it's over here, okay, or the highest wave vector. So there's the Fermi momentum, okay, which is the momentum of this electron. Okay. And this from here clearly is equal to 3 pi squared n to the 1/3, and then we can find the Fermi velocity, which is equal to h bar over m. Okay, so you want h bar kf to give you the momentum, the true momentum divided by m. So this is going to be h bar over m 3 pi squared n. So let me give you some order of magnitudes here. Okay, so for a metal, we take n to be around 10 to the 22nd, 10 to the 23rd. Okay. And then for the mass, of course, you should replace it. If we're considering the periodicity of the lattice, we should replace the mass by the effective mass of the electron instead of the solid mass. But if I use the free space mass, okay, we find out that this is approximately on the order of several electron volts, okay, up to a factor that's equal to the effective mass. Okay. And then this one, like this velocity thing, is on the order of 10 to the 8th centimeters per second, and this should be comparable to something you know from semiconductors. Right? We know that in silicon, the highest velocity that an electron goes to is about 10 to the 7th centimeters per second. The reason here that it's so high here is because of this n, which means that there are many more electrons, so the Fermi energy is much higher. And then this one, if I did the calculation, this comes out to be about 10 to the minus 8 inverse centimeters. Okay, so these are the relevant scales that we're talking about. But this is the Fermi. This is what's happening at 0 temperature. Okay, and I can draw because in the free electron picture, we replace everything with a simple quadratic energy diagram. And the material is completely taken to be isotropic because it's basically free space. So now, if I draw in momentum space, what this looks like. Okay. So kx, ky, and kz. In momentum space, we have basically a sphere, which is the Fermi sphere. And at 0 temperature, the Fermi sphere is very sharp. Okay. The sphere is completely packed, and there's nothing outside. So this is the sphere at 0 K. Okay. So now, what happens at finite temperature? Well, from here, it tells you that at finite temperature, we have some possibility for occupation beyond the Fermi energy, and that's coming from thermal excitations. Right. So the effect of having a finite temperature, if I draw this in the wave number space, K space, is that the Fermi sphere now is no longer so sharp. It becomes a fuzzy thing, right? So the boundary is no longer well defined, and we only know that the electron is roughly going to all lie within within kBt from the sphere, statistically speaking, right? So that is the at slightly above 0 K. Now, what's good about fermions is this exclusion principle tells us that if we have a packed system like this, then an electron to be excited above the Fermi energy, it can only be excited directly. There's no chance of it going to this state first and then to this state. So it cannot be excited in succession. And so the energy needed to excite, say, this electron over here above the Fermi sphere, above the Fermi surface, is maybe so much. Whereas to excite an electron over here above the Fermi sphere is maybe only about this much. And of course, now this makes this kind of excitation much more energetically favorable when temperature is low. So at low temperature, we can roughly say that what happens to a Fermi sphere is we still have most of the electrons over here. They're still frozen. They don't contribute to anything. But about KBT around the Fermi energy, we have some possibility of excitations, and these are the active electron. Okay? And the active electron has roughly this kind of behavior. Okay? So that's the normal metal, the normal phase of the metal. Now, since we said before that the isotopic effect hints at us that there's something to do with the lattice vibration in superconductivity, and so we need to look at the phonon spectrum. And there's a concept called the Debye sphere, okay, which I'm going to move on to next. So, phonons. Remember, when we studied phonons in this course, we told you that we started from a vibrating chain, right? A chain of atoms, and we quantized the vibration. And the Hamiltonian, the quantized Hamiltonian looks something like, there are multiple modes. So a summation over, I'm going to use Q to denote the wave number for phonon. Summation over Q in 1D. H bar omega Q. A dash Q. Okay. And of course there's some 0-point energy which we will consider today. Okay. And this for phonons, you probably have seen this dispersion diagram, this omega Q diagram. Which relates the frequency of the phonon to its wave number. And that roughly looks like, okay. So in 1D, this energy diagram, you can have positive and negative Q. So this, in this direction, this is negative Q direction. This is Q, okay? And we have something that looks like this. Okay. Professor, did we talk about this?
Yeah.
Okay. And what's interesting is that close to a really low momentum, the phonons roughly have a linear omega Q diagram, which is to say that there is a well-defined velocity of sound, and that is just equal to, the velocity of sound is just equal to omega over Q. Okay. So that's this linear relationship here, and as you go above, dispersive effects become more dominant. You have the velocity the phase velocity and the group velocity differ quite a lot over here. So the concept of the Debye sphere. Oh yeah, and also what is from the in the Q space. Okay, we're drawing the omega Q diagram in what's called the first Briand zone, right? And the boundary of the first Briand zone is where? Right, 2 pi over A, right? And A being the lattice, the spacing between lattice sides. And for a solid, what is that, roughly speaking? That's, yeah, something like below a nanometer. And so it's 10 to the 10 to the minus 10. A is on the order of 10 to the minus 10 meters. Okay. No, this is not the Bohr radius. This is the lattice. I mean, if you think about it should be much bigger than Bohr radius, but it's not so high as nanometers. Yeah, yeah. So as I was saying, this is on the order of 10 to the minus 10 meters. So we find that the Q, the highest possible wave vector for the phonons is on the same order as that of the electron at the top of the Fermi sphere. Right? But phonons have a much lower energy because of this diagram. It's not quadratic. It's something like sinusoidal. Right. So what the device sphere is that we're going to completely ignore the structure of this diagram and just replace it by a simple linear relationship like this. And so instead of having this, we have again a sphere, and I'm moving to 3D now. So we again have a sphere in Q space. And once again, we relate the size of the sphere to the total number. But what is the total number this time? Well, these are called acoustical phonons. Maybe 2C after that. These are called acoustical phonons, and they are attributed to each lattice site vibrating. So the highest possible frequency that you can have is that adjacent lattice sites are moving out of phase from each other. Okay. Maybe you have heard about this in some other courses. There's also the optical phonons, okay, which are something like up here, and their omega Q diagram is roughly flat. Okay. These optical phonons, they come from the structure within each cell. Okay. So if we think about the atomic chain as these masses on springs, okay, and each mass is a cell. Okay. It's a cell in the crystal lattice, and within the cell there might be some more structure to it. It might not be just a single atom inside of the cell. So if those things start vibrating, then we go to this optical branch. But we're considering this acoustical branch now, and the longitudinal acoustical branch. So it follows that the number of modes in the acoustical branch is equal to the number of lattice sites per unit volume. So we can write lattice size by Ni, and that is basically the number of ions. If we're thinking about a solid made of a single kind of atom, okay, the number of ions, which is not necessarily equal to the number of electrons per unit volume, because the ions might have maybe 2 or 3 charges. But let's take it to the single charge now. So the number of ions per unit volume is the same as the number of free electrons when we did the calculation for Fermi. Okay, so we can relate this simply by writing N is equal to 1 over 8 pi Q. Okay, so why is this? Well, basically, we're saying that each of them is separated by like L over 2 pi, and so each of them in one dimension are separated by 2 pi over L. The delta Q is something like this. So in K space, if we think about 3 dimensions, each of them occupy a cell, a small block of size 2 pi cubed over L cubed, which is omega. And since we're counting per unit volume, things omega cancels. So what we're doing here is we're taking a sphere in Q space, dividing it by the number, by the area per unit cell, okay, per mole, dividing it by the volume per mole, and that we're equating this to the total number of moles there should be. Okay. So this fixes QD for you, which is the size of this device sphere. And based on the Debye sphere, we get that h bar Bs qd is equal to h bar omega d. This is called the Debye frequency, and this is called the Debye energy, which is the energy of the highest energy of the most energetic phonons, most energetic acoustical phonons. Now, this, to give you an order of magnitude, okay, the QD, we said this is also roughly about, QD is roughly 10 to the minus 8 inverse centimeters, and omega D is on the order of 30 millielectron volts. Okay. Yeah, that's roughly it. And
so those dimensions don't match today. If you look at the third equation down, the dimension on the left hand side and right hand side don't match. Or
why not?
Nu is frequency.
Oh no, nu is sound velocity. Sorry.
Sound velocity.
Yeah, and to get the 30, it should be actually 35. So to get this number, I use the sound velocity in aluminum, which is about 6,000 meters per second. Okay. So this is roughly the scale that we're talking about. So now, if we consider that the lattice is vibrating, and we consider the possibility of electrons picking up some energy or giving out some energy to the lattice, then our Fermi sphere, even at 0K, is going to be not so sharp as before. It's going to be fuzzy because of the existence of the phonons. But then it's not the fuzziness is not going to be dominated by temperature, okay? Because as I said before, the highest temperature of the classical superconductors is about 20 Kelvin. So KBT at about 20 Kelvin. Okay? This is roughly only 1 millielectron volt. Okay? So we see that the phonon is much more energetic than the thermal, or the average thermal energy. So the Fermi sphere, due to the existence of phonons, it's going to look like that original sphere at 0K, but then it's going to be more fuzzy than what we saw from temperature consideration in this temperature range. And this fuzziness is dominated by the highest possible energy for phonons. Okay. So this is the kind of this is how we should describe the electrons in a metal at this temperature when we consider lattice vibrations. Okay. So it's still a mostly frozen Fermi sphere with some uncertainties as to which on the boundary. Okay. And that uncertainty is of the order of 35 millielectron volts, whereas the Fermi energy is roughly in the order of electron volts. So this is the energy scale that we're thinking about. Now, if we use this 35 millielectron volts, and we think about out of all these electrons over here, that's close to the Fermi surface, what is the spread of wave number? Okay, so we want to look at a delta K. Okay. So to compute the delta K, we basically add the photon energy to the Fermi energy. Okay. So E Fermi plus h bar omega d, and we invert this to get K, and then we subtract the Fermi momentum. So this is 2m over h bar squared, this into the 1/2. And we find that this value is roughly equal to 10 to the minus 6, inverse meters. So this is about a micron, inverse micron. 1 inverse, sorry, this is 10 to the minus 5. Let me take a look at my notes. Okay, So the delta K turns out to be about 10 inverse micron. Okay. Now, why do we consider this delta K here? Because what's going to happen is if I were to sum over these active electrons and make a wave packet, okay, this delta K is going to give me the spread, roughly the spread in momentum states or wave number states. Right? And from the uncertainty principle, we know that, or just from Fourier transform, we know roughly that delta K and delta R, which is the spread, the spatial spread of the wave packet, is on the order of 1, or h bar divided by h bar, right? Going from P to K. Okay, so this tells us that if we have a wave packet assembled from these possible free electron waves, then the spread of the packet is going to be on the order of 0.1 micron. Delta R is roughly 0.1 micron. Okay. So this is the highest possible delta K. The lowest possible delta K at some temperature is dictated by this KBT, right? So if we were to do a calculation by plugging KBT here, we find that the lower bound for delta K is on the order of delta K minimum at some temperature. This is T equals to about 20 Kelvin. This is on the order of 1 inverse micron. Okay. So we know that if I were to sum up a wave packet over here, then the spread of the wave packet goes from 0.1 micron to about 1 micron. Okay. And what is the significance of this value? Well, it turns out that later when we try to assemble these two electron wave packets, okay, we can think about them as being one particle with the reduced mass, having roughly the same spread of wave function. Okay? It tells you that roughly these two electrons are going to be separated by this much.